Okay, so this lecture is about titration. The next lecture that'll be up will be about KSP. Excuse me. So you already know, and you've seen in lab, that when we do a titration, the purpose of this titration is to neutralize an acid and a base in an acid-base neutralization reaction. And there's many different ways we can test the pH to make sure we've met that neutralization point. We can use color indicators such as methyl blue, such as methyl red, phenolphthalein, pH meters. pH meters are not a color indicator. Sorry, went ahead of myself. At any rate, many different ways that we can test the pH to see if we are at neutralization, past neutralization, and what's happening. So when we know a substance or a solution has reached the equivalence point means that the moles of the acid and the moles of the base are equal. Okay, so it's not necessarily volume or concentration are equal. Sometimes that happens by coincidence, but moles of each individual acid and base are equal. So when we start off learning about titration, we always start with strong acids and strong bases. And the reason we do this is because they're relatively simple. Strong acids completely ionize and strong bases completely dissociate. So what does that mean? That means if I have hydrochloric acid, 100% of the hydrogens and chlorines will leave their compound to become hydrogen ions and chloride ions. Same thing with a strong base. If I had, for example, sodium hydroxide, then I would see that all the sodium ions are in solution and all the hydrogen ions are in solution. When we reach this equivalence point, the ratio of moles are equal. So what do we mean by that? So if I look at this picture here, okay, what I'm looking at is that there's only hydrochloric acid ions present, so hydrogen ions and chloride ions. And if I look here, what I can see that there are sodium ions because we're talking about HCl, strong acid, plus NaOH, strong base, and they're going to completely ionize. So once I introduce a sodium ion into solution, it is going to form a bond with a chloride ion, and the hydrogen from the chloride ion and the hydroxyl from the sodium hydroxide will form and come together to form water. If you remember, it's acid plus base yields soluble salt plus water. Just before the equivalence point, the pH increases at an exponential rate. We get this really, really nice titration curve. So the pH, no, pen, thank you. The pH is increasing. Wow, that's a really bad arrow. Sorry about that. So the pH is increasing. We meet our equivalence point where the moles are equal, and then we get this huge upshoot of pH because all of the hydrogen ions in solution are at a larger amount. The takeaway from this particular topic is that at the equivalence point, moles of acid equals moles of the base. That doesn't mean their volumes are equal. That doesn't mean their concentration is equal. All it means is that the moles equal themselves. and the solution contains only water and the salt present. Now, I want to make something very clear. The salt is made up of the cation of the base and the anion of the acid. So, if I had, I want black, HCl plus NaOH yields NaCl plus H2O. If I have that, then what that means is the cation of the base, the anion from the acid is going to make up that soluble salt. What is left is the hydrogen and hydroxide to form water. As we increase more base, you guys saw me do this if you were in my Tuesday lab. If not, you did it yourself in your Thursday lab. As you added more base, there was no more acid to react with the base. There were no more hydrogen ions to react with the hydroxide in the base. Therefore, more hydroxide ions stayed in solution. So the pH rose at a rapid succession. All right. And then it eventually levels off to where we could just keep adding and adding and adding and adding, but it's not really going to affect the pH. It just, it just stays really, really strongly basic in solution. Okay. So once we reach the point of equivalence, there is no longer any hydrogen ions to react with the hydroxide ions in the base solution. Once we're past that point, we have an exponential increase in pH, meaning numerically the number gets high, meaning it becomes much more basic. The caveat to this is everything we've just talked about is a strong acid and a strong base. Well, weak acids with a strong base are a very different story. Okay, so when we talk about this, we have to understand a few things. The first thing is that a weak acid will only partially ionize, roughly 5%, but a strong base, 100% dissociates. All right, so the conjugate base of the acid affects the pH when it is formed. The conjugate base of the acid. If you remember, weak acids, for example, acetic acid, my brain is working faster than my finger can write. Okay, the conjugate of this acetic acid is the acetate anion. Okay, this is the conjugate right there. So when that conjugate base of the acid is formed, it affects the pH. The equivalence point is still 7, pH is 7, and we can use phenolphthalein as an indicator. That's the stuff I used in lab when the solution turned pink. Okay, if you remember that. The phenolphthalein tests for the presence of hydroxide anions. It tests for OH minus in solution. And if it's testing for the OH minuses in solution, the hydroxide anions in solution, that means they're in there because there's no longer any more hydrogen ions to counteract the hydroxides. They're used up. So that means I have excess hydroxide ions. So as soon as the hydroxide ions stay in solution, the phenolphthalein will turn pink instantly. We've already looked at weak acid-base equilibrium ad nauseum at this point, okay? So just remember, the takeaway here is that when we titrate strong bases with weak acids, we can use Ka's, concentrations of the weak acid, concentrations of the weak conjugate base, to calculate the hydrogen ion concentration, which is the pH. In fact, if we know the exact pH and volume, we can calculate anything that has to do with the weak acid at any given point in the titration. So we could look at different values at different places. So what this graph is showing you here, and again, you don't have to memorize this, you just need to kind of understand it and be able to talk about it. The equivalence point for all of these different examples is the same, 50 milliliters of sodium hydroxide. So if you look at the initial pHs, this much must be, the red line, must be a much stronger weak acid than, say, for example, this weak acid here. Okay, remember, we have our weak acids, but there's still the range of weak acids. So at any point, we can calculate all these things and see really what's happening. If we were to compare all these to the strong acid, which is the black line right here, clearly the pH is significantly lower and the equivalence point is reached much more quickly than of the other ones. And there's a much more sharp upheaval in pH. Titration of a weak base with a strong acid is exactly the same, but opposite, right? So if we have a weak base in the flask and the strong acid, maybe hydrochloric acid with NH3, so if we had maybe our strong acid is maybe HCl, and our weak base is maybe NH3, okay? The weak base would be in the flask, and the hydrochloric acid would be in the burette, and that would be our titrant. What we would see is the exact same thing. We would see a reverse shift in our titration curve. Instead of being your typical S, right, we would see the reverse, almost like a Z, all right, because we're starting with something that has a very high pH, and as we add the strong acid, the pH is going to drop significantly eventually to becoming a very acidic solution. The equivalence point is still the same. It doesn't matter if we're titrating weak, weak, strong, 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 weak, weak, strong. None of that matters. What matters is that at the equivalence point, right there, the moles of the acid and the base are equal. Also in this case, using the phenolphthalein is not a good idea, because if I put the phenolphthalein in my flask, yeah, it's going to turn pink immediately because there are 100% the hydroxyls, the hydroxy groups in the flask. So, and that's what it's testing for. So a better choice would be a methyl red indicator. We don't use that a whole lot in Gen Chem 2. You will be using that more in organic. But methyl red indicator is just another pH indicator. And it's good to use when we're titrating with an acid. So phenolphthalein is put in the flask of the acid when you're titrating with a base. Methyl red is a good choice to put in the flask when you're titrating in the burette with an acid. Polyprotic acids, this is why we did the Coke demonstration. Now I had to boil the Coke for roughly 30 minutes. Once it got boiling, which took about 5 minutes, I had to boil for an additional 25 minutes. That was to get rid of the carbonate that was in there that makes it bubbly and you know, carbonated, because that can also react with our reaction. So we had to get rid of all that, those gases that were soluble in the solution. Once I got rid of all that, we were simply testing the acidity of the phosphoric acid, which is in the Coca-Cola soda, and that's H3PO3. And what we will see is that there's actually 3 titration curves. The first one is the first deprotonation, and we see that here. That's the first hydrogen coming off once it's come off. And then we see this kind of second one here, so we're left with HPO3 2-. Now in our graphs, and which is true for most labs, unless you have very, very specific, very calibrated equipment, the curve you see is not going to be much with that, you know, kind of third hydrogen getting kicked off. You're going to see really good, 2 really good curves, and the third one is going to look like a little blip. And we saw that exactly. If you recreated your data points in your Excel spreadsheet for your lab reports, you probably saw that better than what we printed out as the actual graphs. So this is the end of the titration lecture. The next lecture that's going to be put up is going to be about KSP. We have a new K to introduce. So far we've had KC, KP, KA, KB. Now we're going to have KSP, and it has to do with solubility. It is still the same as everything we've already done, products of a reactants, but there's a little bit of caveat that has to go with it. Okay, so I have this morning, very early, I uploaded the worksheet that I want you to print out and bring to class. The key is also uploaded. It's actually labeled under aqueous equilibrium. Bring that to class tomorrow. We're going to work on the pH stuff tomorrow, and then over the weekend I will post a KSP lecture, and then we will continue on with that same worksheet on Tuesday. If you have any questions, as usual, let me know. Shoot me an email, and I will see you guys tomorrow. I don't know what's happening right now.